Now it is fine. Now it is fine. Am I audible? Okay, now everything is fine now. Shall we start? Shall we start the session? Everything is fine. Please type in a chat box. Everything is okay. Shall we start the session? Okay. So today we start a new subject, which is a fluid mechanics. And guys, this is a one of the most fundamental and important subject for mechanical engineers, chemical engineers, civil engineers, at the same time students who are planning to appear in XC examination and the PI examination, right? This is very fundamental subject, but most of the students find difficulty in this particular subject. The reason is vast syllabus, right? Fluid mechanics syllabus is very vast, but if you know the syllabus, or if you understand the syllabus carefully, then you will find this is the most easiest part, right? So first what topics we will cover today. First we will discuss what topics we will cover today. So first we will discuss about the introduction, then we will discuss about the difference between the solid and fluid, what are the differences between solid and fluid. Then we will discuss some fundamental properties related to the fluid, and after that we will discuss a very important law, which is Newton's law of viscosity, right? In most of the examination you are getting question from the Newton's law of viscosity. So Newton's law of viscosity is a very important topic when you when we are talking about the first unit, which is a fluid property. Okay, now first discuss about the syllabus, right? Because this subject is common for the mechanical engineers, chemical engineers, civil engineers, right? So first discuss about the syllabus. So if I'm talking about the mechanical syllabus, so this is the mechanical syllabus from GATE point of view, right? From GATE point of view, this is the mechanical syllabus. So if you see fluid properties, fluid statics, then forces on submerged bodies, stability of floating bodies, control volume analysis of the mass, momentum and energy equation, fluid acceleration, differential equation of continuity and momentum, Bernoulli equation, dimensional analysis, viscous flow of incompressible fluids, boundary layer, elementary turbulent flow, flow through pipes, head losses in pipes, bends and fittings, and basic of compressible fluid flow. So guys, basic of compressible fluid flow, actually it is a part of the application of the thermodynamics, but it is given in the fluid mechanics syllabus, so no problem. But most of the time we are dealing with compressible fluids in the thermodynamics. So basically this basics of compressible fluid flow is a part of the application of the thermodynamics, right? Now if I'm talking about the civil syllabus, right, might be most of the student here from civil background. So if I'm talking about the civil syllabus, so this is the civil syllabus for fluid mechanics, right? Here hydraulic machines is not considered, at the same time that open channel flow is not considered here, right? This is purely fluid mechanics syllabus. And if I'm talking about the chemical syllabus, right, this is the chemical syllabus, right? Might be some of students from the chemical background also here. So for those students, this is the chemical syllabus. And if you find, okay, either you are from the mechanical background or civil background or chemical background, you will find there are certain topics which are common in all the branches, right? Only few topics are there, that some topics might be some topic in chemical, but that is not part of the mechanical syllabus, that is not part of the civil syllabus, but most of the syllabus is common for all the three branches. If I'm talking about the 𝐂𝐸 syllabus, right? If I'm talking about the 𝐂𝐸 syllabus, so this is the 𝐂𝐸 syllabus, right? You already know 𝐂𝐸, right? In 𝐂𝐸 paper, there is a one separate section for the fluid mechanics, right? And that consists 35 marks question, 35 marks question in that section, right? One marks 9 question, and 2 marks there is a 13 question. So total there is a 22 questions, right? 22 question, 13 marks, 2 number, 13 marks, just 1 minute. Total in 𝐂𝐸 paper, total number, that is a 35, and out of this 35, 9 questions, 1 marks, and 12 questions from 2 marks, right? And this is the complete 𝐂𝐸 syllabus. This is the complete 𝐂𝐸 syllabus. If you see here, section number 1, flow and fluid properties. Section number 2, kinematics of the fluid motion. Section number 3, integral analysis for a control volume. Now come to the section number 4. Section number 4 is a differential analysis. Section number 5, dimensional analysis, and section number 6 is the internal flow. Section number 7, Bernoulli equation and its application part. Also this section consists potential flow. And section number 8, that is the external flow. In this particular part, boundary layer theory, Prandtl boundary layer equation, lift and drag part. So that external flow consists those part. Now, content of the course. Let's talk about the content which I delivered in this particular course. So we will start from the fluid and fluid properties, right? We will start from fluid and fluid properties. So this is the first chapter, you can say, right? Or first module, you can say. Second chapter or second module is pressure and pressure measurement. Third chapter is hydrostatic pressure force on the surfaces. So if I am talking about the hydrostatic pressure force calculation on the surfaces, so there are two type of surfaces, right? One is a planar surface, and second one is a curved surface. So whenever we are dealing with this topic, right, hydrostatic pressure force, so we calculate the hydrostatic pressure force on two types of surfaces. One is the planar surface, and another one is a curved surface. Right. Next topic is a buoyancy and flotation. This is one of the important topic. After that, we will discuss about the fluid kinematics. Right. This is a part of the this is part of the fluid statics. Right. 1 to 4. This is the part of the fluid statics. After completing fluid statics, we will discuss about the fluid kinematics, right? After fluid kinematics, we will discuss fluid dynamics, and this fluid dynamics part is very, very important. Almost every year you are getting question from fluid kinematics and fluid dynamics, right? Now see, if I am talking about the fluid dynamics syllabus, in fluid dynamics syllabus, the Bernoulli equation and its application, Bernoulli equation and the application part. So if I am talking about the application part, right, in application you are getting venturi meter, orifice meter, pitot tube, right? So almost every year you are getting the question from Bernoulli equation and application part. After that we will discuss the RTT theorem, which is a Reynolds transport theorem. This is a This part is important for the potential. This part is important for the X exam, right? RTD, Renault Transport Theorem. After that, we will discuss about the linear momentum equation and the angular momentum equation, right? And its application. Chapter number 7 is a internal viscous flow. In internal viscous flow topic, right, or in internal viscous flow chapter, you are getting topic related to pipe flow, plain Poiseuille flow, and the 𝐂𝐚𝐴 flow, right? After completing the internal viscous flow, then next chapter is the external viscous flow. External viscous flow. In external viscous flow, there are two very important topics. One is the boundary layer theory, and next one is the lift and drag, right? Boundary layer theory is very important. And see, chapter number 9 is the elementary turbulent flow, right? We are not dealing turbulent flow in a vast manner, because in the syllabus it is specifically mentioned elementary turbulent flow. So we will focus about the basic things related with the turbulent flow, right? After completing the elementary turbulent flow, the next chapter is a dimensional analysis, right? Dimensional analysis is important in heat transfer subject also. Not only in the fluid mechanics, it is important in the heat transfer subject also. And after that, last topic is the potential flow. So this is the syllabus of the fluid mechanics, right? And in this syllabus, hydraulic machines is not mentioned, right? Hydraulic machines is not mentioned. At the same time, if I'm talking about the civil background student, that open channel flow is not mentioned, right? So this is your complete content of the course, or this is the syllabus also. Now, if I'm talking about the weightage, right? If I'm talking about the weightage, so see, if I'm talking about the weightage in gate examination, right? Weightage in gate examination. So guys, every year you are getting question from fluid mechanics, and if I'm talking about the average weightage, right? So average is around, we can say, 6 to 8 marks, right? That weightage of this subject in gate examination is 6 to 8 marks. If I'm talking about the engineering services examination, so in engineering services examination, there is two sections now. One is a pre-section and second one is a mains. So if I'm talking about the pre, right? If I'm talking about the pre-section, in pre-section, every year you are getting question from fluid mechanics 6 to 20 marks, right? In pre. And if I'm talking about the mains paper, so in mains paper, it is a part of the paper 1. Actually, in mains paper, there are two papers. One is a paper 1 and second one is a paper 2. The paper 1 is related with the thermal and fluid science related subject, and paper 2 is related with the design subject. So in mains, it is a part of paper 1. It is part of paper 1. And in this paper, you are getting question from fluid mechanics around 40 to 50 marks, right? Mains paper is a complete conventional paper. So in mains paper, fluid mechanics is a part of paper 1, and you are getting 40 to 50 marks question from that paper number 1, right? Now see, next important thing is books, right? Next important thing is books, right? Which books, sir, we prefer for the fluid mechanics subject? So there are number of books, right? There are number of good books, I can say. The first book is a Fluid Mechanics by Sanjal and Simbala. This is one of the good book if you want to take a feeling of a subject, right? Then this book is a very good, because in this particular book now there are number of real life application is present in this book, right? So this is one of the good book for the fluid mechanics, 𝐂𝐤𝐿 and 𝐶𝐬𝐵𝐬𝐿. The second book is Fox and McDonald, right? This is also one of the good book, right? Most of the time you are getting direct question from this book, Fox and McDonald, because in IITs all professors also recommend this book, that is Fox and McDonald. Next book is Franken and White, right? This is also a good book if I'm talking about the foreign author, right? So these three books is related with the foreign author, and this book Fluid Mechanics by Som and Biswas, this is related with Indian author. So in Indian author, this is one of the good book, right? So you can prefer any book, right? And I will suggest this 𝐂𝐤𝐿 and 𝐶𝐬𝐵𝐬𝐿. This is a very, very good book, because in this particular book, right, application is mentioned, number of application, number of real life application is mentioned in this book. So this is one of the good book related with the fluid mechanics. Now, if you want to practice number of questions, right, if you want to practice number of question, then this is the book, right, that you must have. This book, in this book there are number of solved problems, right? In this book there are number of solved problems, that is fluid mechanics and hydraulic machines by 𝐂𝐤𝐴𝐵𝐬𝐿. So if you want to practice number of problems, number of numerical problems, right, from gate point of view, then definitely this is one of the good book, fluid mechanics and hydraulic machines by 𝐂𝐤𝐴𝐵𝐬𝐿, right? If you use the internet power, right, if you use the power of internet, then you can find this book in Google also, right? Soft copy of this book you can find in Google also, right? So this is related with the book. Now, what I want from you guys, just 1 minute, I'm not able to see the chat. Just 1 minute now. Okay. Definitely we will do some questions also, and also I'm giving some assignment problem, don't worry. I'm also giving some assignment problem in the Telegram group, so don't worry about the practice questions. I will give the number of practice questions. Okay, so see, try to attend the class regularly, right? These things I want from you guys. Try to attend the class on regular basis. Next is maintaining a good notebook, right? This is your master notebook, right? Bring a very good copy and maintain a very good notebook, and that book I can say this is your master notebook. After that, at the end of the class, you can ask any question related with the subject. If you have any doubt or if you have any query, you can ask at the end of the class. And try to maintain the short notes parallelly, right? Try to maintain the short notes parallelly, right? So there is no separate time is required for the short notes, right? So try to maintain the short notes on regular basis, right? We will try to cover the 𝐿𝐶 part also, don't worry. We will try to cover the 𝐿𝐶 part also. Actually in mechanic, if you are from mechanical background, so there is not much difference between the mechanical and the 𝐿𝐶, right? Except one or two topics. One topic is the potential flow. Potential flow is not a part of mechanical syllabus. It is especially mentioned in the 𝐂𝐸 syllabus. And the second part is the Reynolds transport theorem. Right, Reynolds transport theorem is also not mentioned in the mechanical syllabus, but it is a part of the 𝐂𝐸 syllabus. But anyways, the Reynolds transport theorem, right, when you study only mechanical syllabus, still we are using the Reynolds transport theorem over there. So there is no problem, right? We will cover the 𝐂𝐸 syllabus also, so don't worry about that. I think in the channel description it is mentioned, right? Right, in the channel description the Telegram link is mentioned, so from there you can join the Telegram. Okay. Okay, so let's start this subject. Let's start the fluid mechanics. Right, again I'm telling you guys, whatever the concept is using in the fluid mechanics, those concept is used in the convection heat transfer also. If you are from the mechanical background or if you are from the chemical background, right? So whatever the concept we use in the fluid mechanics, those concept is used in the convection heat transfer also. So fluid, without knowing the fluid mechanics, it is difficult to understand the especially convection heat transfer. You understand the conduction heat transfer, you understand the radiation heat transfer, but without knowing the fluid mechanics or without knowing the concept of the fluid mechanics, it is little bit difficult to understand the convection heat transfer. So from the heat transfer subject point of view, also it is one of the important subject. Okay, so let's start the subject. Now come to the, see, if I'm talking about the fluid mechanics, actually fluid mechanics word is made of two terms. One is the fluid, second one is the mechanics. So if I ask you guys what is the mechanics, right? If I ask you what is the mechanics, what is the mechanics? Can anyone tell me what is the mechanics? What is the mechanics? Can anyone tell me what is the mechanics? This fluid mechanics is made of two words, fluid plus mechanics. So forget about the fluid right now. If I ask you what is the mechanics, so can anyone tell me what is the mechanics? Can we define the mechanics? So we can define the mechanics in this way. Mechanics is the branch of science. Mechanics is the branch of science in which we deal with the bodies, in which we deal with body or bodies, rest or in motion, under the influence of external effects. So mechanics is the branch of science in which we deal with the body or bodies, rest or in motion under the influence of the external effects. And what are those external effects? So that external effect may be force, that external effect may be moment, So if someone asks you what is the mechanics, because in future you are dealing with the engineering mechanics, in future you are dealing with the mechanics of material or strength of material, right? So what is the basic definition of the mechanics? So basically in mechanics we are dealing with the bodies, right? We are dealing with the body or bodies, right? That body may be rest or in motion under the influence of the external agent or external effect, and that external effect may be force or moment, right? Now see, if I'm talking about the body, right? So mechanics is the branch of science in which we deal with the bodies either rest or in motion under the influence of external effects, and that external effects may be force or moment. So see, if I'm talking about the body, the body may be solid body, the body may be solid body, the body may be solid body, the body may be fluid body, the body may be solid body, the body may be fluid body, right? क्या बोल रहे हैं? हिंदी में क्लास नहीं होगी, यहां पे इंग्लिश में क्लास होगी. सुमित, right? Now if I'm talking about the body, so body may be solid body and body may be fluid body. Now if I again divide this solid body, again I'm dividing this solid body in a two types of body. One is a rigid body, and second one is a deformable body. The solid body is further classified as a two type of body. One is a rigid body and second one is a deformable body, right? Now if I am considering the rigid body in mechanics, again I am repeating, in mechanics, if I am considering the rigid body, then that particular subject is known as the engineering mechanics. So in engineering mechanics, we are dealing with the rigid body, right? In engineering mechanics, we are dealing with the rigid body, right? And mechanics of deformable body is known as the strength of material or mechanics of material or mechanics of solid or mechanics of solid, right? So if your body is a rigid body, then the mechanics of that rigid body is studied under engineering mechanics subject. If your body is a deformable body, then mechanics of deformable body is studied under the strength of material subject or mechanics of material subject or or mechanics of solid subject, right? That all the subjects are same only. Now can anyone tell me what is the difference between the rigid body and deformable body, right? Any student can tell me what is the difference between the rigid body and the deformable body? Can anyone tell me what is the difference between rigid body and the deformable body? Anyone? Can anyone tell me what is the difference between rigid body and the deformable body? Can anyone tell me? Rigid, no changes. No changes means shape will not change, dimension will not change. What is the meaning of the rigid? Changes its shape. Okay. Very good. Okay. Now see, if I'm talking about the rigid body, see guys, if I'm talking about the rigid body, what is a rigid body actually? Right? Rigid body is a body in which no change in relative position of the particle under the action of forces and moments. Right? So see, let us consider a random body, right? Let us consider a random body. So this is a random body, right? And this body is made of number of particles, right? This body consists number of particles. So let us consider two particles. Let us consider two particles. So let us consider this is the particle number A and this is the particle number B. This is the particle number A and this is the particle number B. Right? So this is any random body. This body consists number of particles. So out of those number of particles, I am considering the two particles. So let us consider particle number A and particle number B. Now distance between the particle number A and particle number B is, let us consider, that is a x. The distance between particle number A and particle number B, let us consider that distance is x. Okay, now before applying the external agents, or before applying the forces and moments, the distance between these two particles are distance between these two particles is x. Now I am applying the forces. So let us consider this is the force F1. Let us consider this is the force F2. Let us consider this is the force F3. I am also applying the moment. So let us consider this is the moment, that is M. Right? Moment M1. I am also applying another moment. So let us consider this is the moment M2. Right? That means this body is subjected to number of forces and number of moments. Now, if this body is a rigid body, then x is constant. If this body is a rigid body, then the distance between two particles does not change under the action of the forces and moments. Such type of body is known as the rigid body. So in case of the rigid body, the relative position of the two particles does not change. That means this x is always constant. Getting my point? Right? So if x is constant, such type of body is known as the rigid body. Such type of body is known as the rigid body. But if x is not constant, if x is not constant, if x is changing, and how the x changing? So definitely if there is a significant deformation, happen, then definitely x will change. Right? In such cases, or in that particular case, that body is not rigid body, then that body is a deformable body. Right? So if x is not constant, then such type of body is the deformable body. Then such type of body is known as the deformable body. So it is very simple definition of the rigid body. What is a rigid body? Rigid body is a body in which no change in relative position of the particle under the action of forces and moments. Such type of body is known as the rigid body. And if change occurs, if change in relative position of the particle occurs, then such type of body is known as the deformable body. Right? So mechanics of the rigid body is studied under engineering mechanics subject, and the mechanics of the deformable bodies is studied under the strength of material subject. Okay, now why I'm explaining this particular part? You can say, sir, this is a part of the engineering mechanics, or this is a part of the strength of material. But sir, why you are explaining this particular part? Why you are explaining the rigid body concept? Right? Now this in the fluid mechanics, there is a one chapter, right? And that chapter, in that particular chapter, we can say the motion of the fluid particles or motion of the fluid is like a rigid body, right? So in a fluid mechanics, there is a chapter that is a rigid body motion. In a fluid mechanics, there is a chapter that is a rigid body motion. In some books, you are getting that particular chapter in rigid body motion name, and in some books you are getting that particular chapter as liquids in relative equilibrium. Liquids in relative equilibrium. Right? In fluid mechanics, there is a chapter that is called rigid body motion. Rigid body motion. rigid body motion, or in some books you are getting that chapter in the name of liquids in relative equilibrium. Right? Now see, you can understand the rigid body motion from the concept of the rigid body. Right? You can understand the rigid body motion concept from the concept of the rigid body. So what happened in case of the rigid body motion? Can anyone tell me? What happened in case of the rigid body motion? Can anyone tell me? You understand the concept of rigid body, right? You understand the concept of a rigid body. And if I ask you rigid body motion, what is a rigid body motion? So can anyone tell me what is a rigid body motion? Rigid body motion. Can anyone tell me? So in case of the rigid body motion, in case of rigid body motion, in case of rigid body motion, in case of rigid body motion, relative velocity between two fluid particles, relative velocity between two fluid particles is zero. That is the meaning of the rigid body motion. Right? That is the meaning of the rigid body motion. Right? In rigid body motion, the relative velocity between the two particles is zero. Relative velocity between two particles is zero means both the particles is moving with the same velocity. Right? Relative velocity zero means both the particles is moving with the same velocity. That is the meaning of the rigid body motion. Right? Okay. Now, is it clear to everyone? Till this point, it is clear to everyone? Till this point, it is clear to everyone? Tell me. Till this point, it is clear to everyone? Till this point, it is clear to everyone? Okay, fine. Now, we understand the mechanics, right? We understand the mechanics. But now what is the fluid mechanics? What is the fluid mechanics? So guys, we can say fluid mechanics. Fluid mechanics is the branch of science in which we deal with the fluid and its behavior. Right? In fluid mechanics, we are dealing with the fluid that in fluid mechanics subject we are dealing with the fluid and its behavior. The fluid may be static or may be in motion. Right? Fluid may be static or may be motion. So if fluid is static, then that particular branch of fluid mechanics is known as the fluid static. Right? If fluid is static, then that particular branch of fluid mechanics is known as the fluid static. If fluid is in motion, and cause of the motion is not considered, that means cause of the motion is nothing but the force. Right? Cause of the motion is nothing but the force. So if fluid is in motion and cause of the motion is not considered, then that particular branch of the fluid mechanics is known as the fluid kinematics. Right? And if fluid is in motion and cause of the motion is considered, then that particular branch of fluid mechanics is known as the fluid dynamics. So basically, fluid mechanics has three parts. If I am talking about the fluid mechanics, subject, fluid mechanics. Right? Fluid mechanics has three parts. One is the fluid statics, one is the fluid statics, second one is a fluid kinematics, and third one is a fluid dynamics, right? Now in fluid static, fluid is in static condition. Can anyone tell me what is the meaning of this? Fluid is in static. Can anyone tell me what is the meaning of fluid is static? Can anyone tell me? Can anyone tell me fluid is in static? What is the meaning of that? Fluid is static. What is the meaning of that? Can anyone tell me? Right, fluid is static means, fluid is static. Please try to understand. This is very, very important logic. Fluid is in static means the fluid may be stationary. Fluid may be stationary. Fluid may be stationary, or fluid may be moving with constant velocity. The fluid may be fluid moving with constant velocity. Right? Fluid is static means the net force summation F is equal to 0. Summation F is equal to 0. Fluid is static means summation F is equal to 0. Right? So if I am talking about the fluid is in static condition, that means fluid may be stationary. If fluid is stationary, then definitely the net force is 0. If let us consider there is a one object, and you are pulling this object in this direction by applying the 10 Newton force. Also in this direction there is another guys, this also pulling this subject with the force of 10 Newton. So this object is stationary, na? This object is stationary. Getting my point? So in this case, what is the summation F? What is the summation Fx? If I am talking about, if I am saying this is the x direction, so summation Fx is equal to 0, right? So summation F is equal to 0, right? In this case also and in this case also, right? So if fluid is in motion, then we can write that net force is equal to rate of change of momentum, right? We can say the summation, if the object is moving or if the fluid is moving, then we can say summation F is equal to rate of change of momentum. And if I consider mass is constant, then we can say m dv by dt, right? And if your object or fluid is moving, in this case object is fluid. So in this case, if fluid is moving with constant velocity, so velocity is constant, so dv by dt is 0. So we can say the summation F is equal to 0. Summation F equal to 0. Right? So again I am repeating guys, fluid is static means fluid may be stationary or fluid may be moving with constant velocity. Fluid is static doesn't mean fluid is stationary. The most of the student make mistake here. Fluid is static means fluid may be stationary or fluid may be moving with some constant velocity, right? Now in fluid statics, fluid is in static condition. In fluid kinematics, fluid is in motion. Fluid is in motion, but cause of the motion, that is force, is not considered, right? In fluid kinematics, fluid is in motion but cause of the motion is not considered, right? That is force. So in fluid kinematics chapter or in fluid kinematics topic, we are mainly dealing with the velocity, mainly dealing with the acceleration, but we are not talking about the forces, because when we are dealing with the fluid kinematics part, we are not dealing with the forces, we are dealing with the velocity, we are dealing with the acceleration part. Now come to the fluid dynamics. In fluid dynamics, fluid is in motion. Fluid is in motion, but cause of the motion is considered. But cause of the motion, that is force, cause of the motion is considered. Right. So fluid mechanics has three parts: fluid static, fluid kinematics, and the fluid dynamics. Okay, is it clear to everyone? Is it clear to everyone? Now come to the next part. In this three, which part have more weightage? So I can say, see, the fluid kinematics, every year you are getting question from fluid kinematics every year, because in fluid kinematics there are some mathematical things, right? Especially vector calculus part, right? So every year you are getting question from the fluid kinematics. See, as compared to the fluid dynamics and the fluid statics, if you are comparing like this, fluid dynamics and fluid statics require more input as compared to the fluid kinematics, right? Fluid kinematics does not require so much input, but every year you are getting question from the fluid kinematics part. Actually fluid statics require more input, because fluid statics have 4 to 5 subtopics, right? In fluid statics we have 4 to 5 subtopics, right? Fluid and fluid properties, that is the first topic. Then pressure and pressure measurement, that is second topic. Then hydrostatic pressure force, that is the third topic. Again in hydrostatic pressure force, hydrostatic pressure calculation on planar surface, then hydrostatic pressure calculation on the curved surfaces, and then buoyancy and flotation. So fluid statics again have 4 to 5 subtopics. Similarly, if I'm talking about the fluid dynamics, again fluid dynamics is so vast, right? In fluid dynamics we are dealing with the Bernoulli's equation application, then Venturi meter part, orifice meter, pitot tube, right? Then there is a linear momentum equation, angular momentum equation, then there is a application of linear momentum equation, angular momentum equation, right? Then there is a pipe flow, right? So fluid dynamics part requires more input as compared to the fluid kinematics, right? Fluid kinematics part is, I can say fluid kinematics part is a fluid kinematics part requires very less input, but you are getting every year question from this particular part, fluid kinematics, right? Okay, now come to the next very important part. What is the difference between the solid and the fluid? So everyone knows the difference between the solid and fluid now. What is the difference between solid and fluid? Can anyone tell me what is the difference between solid and fluid? Right, from the basic we know difference between solid and the fluid. Difference between solid and fluid. Solid and fluid. Can anyone tell me the differences between solid and fluid? Yes, in case of the solid, right? If I'm talking about the solid, so in case of the solid, that intermolecular attraction force between the particles is very strong, right? In case of the solids, intermolecular attraction force between between particles is very strong, right? In the case of the solid, there is a compact packing of molecules, compact packing of molecules. We know this, right? We know this part. In case of the solid, the intermolecular attraction force between the molecules is very strong. Also, the packing is compact, right, in case of the solid. So if you see the solid, if you see the molecules in case of the solid, then there is a packing like this, then there is a packing like this. Yes, we know this difference, na? We know this difference. In case of the fluid, intermolecular attraction force, in case of fluid, intermolecular attraction force is weak as compared to solids, right? So in case of the liquids, arrangement of the molecules is like this. In case of the liquids, arrangement of molecules like this. In case of gases, arrangement of molecules like this. Right. Also, if I'm talking about the solids have definite volume. Right? Solids have definite volume, but if I'm talking about the fluid does not have definite volume. Fluid does not have definite volume. So this difference we know already, right? If I ask 7th, 8th standard student, he also knows this difference between the solid and fluid. But as an engineer, what can add in this difference as an engineer? Right, this is a difference. If I ask you 7th, 8th standard student, he also knows this difference. Whatever the difference we are written here, this difference that student also knows. But as an engineer, what are the differences that you can add? Can anyone tell me? Okay. Now see here. What happened when we apply the tensile load? When we apply the tensile load in solids, what happened? And when we apply the tensile load in fluid, then what happened? Can anyone tell me? When we apply the tensile load, or when we apply the tensile force, then what happened in case of the solid? And what happened in case of the fluid? Can anyone tell me? solid fluid. Okay, so if there is a solid body, let us consider this is a solid body. I am applying unidirectional tensile load here. I am applying unidirectional tensile load here. Then what happened? If I am applying bidirectional tensile load, then what happened? And if I am applying the three-dimensional tensile load, then what happened? Then what happened? Very good, very good, right? So guys, see, if I'm applying the tensile load in solid, that tensile load may be one dimensional, maybe two dimensional, maybe three dimensional. The solid resists that tensile load by showing some definite deformation, right? We know this part, na? We know this part. When we applying tensile load, that tensile load may be one dimensional, maybe two dimensional, maybe three dimensional, right? When we applying the tensile load, solid resist by showing some definite deformation, Is it okay? Is it okay or not? Is it okay or not? When we are applying the tensile load, then solid resists this tensile load by showing some definite deformation. Yes or no? Yes or no? Tell me, guys. But what happened in case of the fluid? What happened in case of the fluid? The fluid resists the tensile load. The fluid resists the tensile load. Tell me, guys. Fluid resists the tensile load. Tell me. Fluid resists the tensile load. Can anyone tell me? Fluid resists the tensile load? No. Fluid never resists the tensile load. The fluid never resists the tensile load. Fluid never resists the tensile load. Fluid never resists. Fluid never resists the tensile load or tensile force. Fluid never resists the tensile load. Right? If there is a bucket of water, right, and you are applying tensile load on some fluid particle. There is a bucket of water and you are applying some tensile load. You are applying some tensile load on a water particles. Right? Water resists to that tensile load. Yes or no? Is water resist that tensile load? No. Water does not resist the tensile load. Are you getting my point? So fluid never resists the tensile load. Right? There is some exception. There is some exception, and that exception is the surface tension force. But surface tension force is a minor force. That is not a major force. Right? We will discuss about the surface tension later on. But right now, right, might be some of students thinking about the surface tension force. Right? Because surface tension force, so it is a tensile force. So yes, sir, that fluid resists that surface tension, sir. Right? So surface tension force is a minor force. Here we are talking about the major forces. So fluid never resists the tensile load except surface tension force. Except surface tension. Except surface tension force. And again I am telling you guys, this is a minor force. This is not major force. This is minor force. This is minor force. Okay, now if I am talking about the compressive load, if I am talking about the compressive load, if I am talking about the compressive load, solid, liquid, solid and fluid, solid and fluid. Now if I am applying the compressive load, or if solid is subjected to compressive load, if solid is subjected to compressive load, when solid is subjected to compressive load, solid resists that compressive load by showing some deformation, right? If solid is subjected to compressive load, solid resists that compressive load by showing some deformation. Showing some deformation, right? If solid is subjected to compressive load, and that compressive load may be 1D, maybe 2D, maybe 3D, right? So let us consider there is a solid body, right? Let us consider this is a solid body. It is subjected to one dimensional compressive load. This is again solid. It is subjected to two-dimensional compressive load. Again there is a solid, and this solid is subjected to three-dimensional compressive load. Right? So when solid is subjected to compressive load, it may be one-dimensional, it may be two-dimensional, it may be three-dimensional. The solid resists that compressive load by showing some deformation. But what happened in case of the fluid? What happened in case of the fluid? Can anyone tell me? What happened in case of the fluid? That can fluid resist one-dimensional compressive load? 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 Let us consider this is the plate, and above the plate there is a fluid, and let us consider there is another plate. Okay, now I am applying compressive load on this plate. Tell me guys, tell me fast. Right, this is the one plate. Above the one plate there is some fluid, right? And again there is some plate. Now I am applying the compressive force, one-dimensional compressive force. So when we are applying the compressive force, when we are applying the one-dimensional compressive force in that fluid resists? No, fluid cannot resist. The fluid cannot resist. Fluid is flowing in this direction. Fluid cannot resist. Fluid is flowing in the x direction. If I am applying the force in a y direction, then fluid is flowing in a x direction. If I am applying a force in a x direction, then fluid is flowing in a y direction. Are you getting my point? And same thing is applicable for the two dimensional. If third dimensional is open, if third dimension is open, so if I am applying the compressive force from two dimension or from the two direction, then third direction is open now, the fluid is flowing on third direction. So the fluid cannot resist one dimensional compressive load, two dimensional compressive load. Fluid cannot resist. Are you getting my point? Everyone getting this point or not? Tell me, guys. Everyone getting this point? So fluid cannot resist one dimensional, two dimensional compressive load. Fluid cannot resist one dimensional, two dimensional compressive load. But what about the three dimensional load? What about the three dimensional compressive load? What about the three dimensional compressive load? What about the three dimensional compressive load? Can anyone tell me what about the three dimensional compressive load? Yes, it resists the, absolutely correct. Very good. Fluid cannot resist one dimensional, two dimensional compressive load, but it will resist three dimensional compressive load. Three dimensional compressive load. Right? So see, if I am giving an example, so let us consider there is a container. And in this container there is a fluid. Let us consider there is a fluid, and let us consider there is a piston. This is the piston. Now I am applying compressive force on this piston. I am applying a force F on this piston. So tell me, guys, this fluid resists this force F or not? Very good. Yeah, absolutely. In case of the hydraulic machines, absolutely correct. Right? Yes, it resists, na? When you apply the force, in this case, when you apply the compressive force, definitely this fluid resists this compressive load. And when you see the see, let us consider there is some particle, and if I see this fluid particle in a large manner, if I see this fluid particle in large manner like this, right, and if you show the free body diagram of this fluid particle, so this fluid particle is subjected to force F, and force F. Compressive force F, and compressive force F. So this is the free body diagram of this fluid particle. Are you getting my point? So guys, fluid cannot resist the one dimensional and two dimensional compressive load, but it will resist the three dimensional compressive load. So I hope you can understand this part. Okay. Is it clear to everyone? Now come to the next difference. Come to the next difference. Come to the next difference. Solid versus fluid. Solid versus fluid. Right. What happened if I am applying the shear load in case of the solid? Right. What happened in case of the shear load when I applying the shear load in solid? In case of the shear load. So solid resist shear load by showing, right, solid resist shear load by showing some shear deformation, by showing some shear deformation, or you can say angular deformation. Shear deformation is also called angular deformation. Right. If you apply the shear load, if you apply a shear load on solids, right, if you apply the shear load on solids, then solid resists the shear load by showing some angular deformation like this. See, if I am talking about this solid body, let us consider this is a solid body. Let us consider this solid body. Right, let us consider this is the solid body. Now I am applying a shear load. I am applying a shear load like this. I am applying a shear load like this. Now what happened here? See here. The solid resists this F by showing some deformation like this. By showing some deformation like this. By showing some deformation like this. This is the angle theta. This is the angle theta. And this is angle theta. Right. So solid resists the shear load by showing some shear deformation. And the shear deformation is nothing but the angular deformation. So this solid object showing some angular deformation like this. Right. And in this case we can say, everyone knows the Hooke's law, na? Right. Hooke's law. And as per the Hooke's law, we can say this, as per the Hooke's law, we can say shear stress, right? The shear stress is directly proportional to shear strain. And shear strain is nothing but the angular deformation. Right, shear strain is nothing but the angular deformation. Yes, very good. Hooke's law is nothing but the shear stress is directly proportional to the shear strain, or stress is directly proportional to the strain. Here we are talking about the shear load or shear stress. So shear stress is directly proportional to the shear strain as per the Hooke's law. Okay, so from this explanation it is very much clear, solid resists the shear load by showing some shear deformation. But what happened in case of the fluid? What happened in case of the fluid? What happened in case of the fluid? So let us consider there is a fluid. This is plate, and in this plate, above this plate, there is a fluid. Okay, and above the fluid, let us consider there is another plate. There is another plate. There is another plate. This is the another plate. Right? This is the bottom plate. This plate is the bottom plate. And this is the top plate. Right? This is the top plate. This is the bottom plate and this is the top plate. Now I am applying shear load on this fluid. Now I am applying the shear load on this fluid. So how I am applying the shear load in this fluid? I am applying the force F on this plate. I am applying the force F on this plate. Right, so in this manner, I am applying the shear load on this particular fluid, which is above the bottom plate. Okay, now see, if you see here, what happened? Now, if I am talking about a layer which is at y is equal to 0, so let us consider this is the x direction and let us consider this is the y direction. So if I am talking about the layer which is near to the bottom plate, or I can say at y is equal to 0, right? At y is equal to 0, at y is equal to 0, what is the velocity? What is the velocity of the fluid particle? What is the velocity of the fluid particle? A fluid particle which is at y is equal to 0, right? I am talking about this fluid particle, na? I am talking about this fluid particle, a fluid particle which is at y is equal to 0. So, my dear, I can say at y is equal to 0, the fluid layer velocity is equal to the plate velocity. At y is equal to 0, fluid layer velocity is equal to the plate velocity. Right? What is the UP? That UP is the plate velocity. Na? UP is a plate velocity. And what is the U? That U is the local fluid layer velocity. Local fluid layer velocity. There are a number of layers, na? If you see here, there are number of layers, na? Number of layers of fluid particles, or number of layers of fluid. See, like this, number of layers. So U is equal to local fluid layer velocity. Right, so at y is equal to 0, that U is equal to UP. That means we can say, na, at y is equal to 0, there is no relative velocity between the plate and the fluid. We can say like this: at y is equal to 0, U is equal to UP. So we can say, na, at y is equal to 0, no relative velocity between plate and fluid. At y is equal to 0, no relative velocity between plate and the fluid. Right? Same thing we can say for top plate also. Right? Same thing here we are saying about, here we are talking about y is equal to 0. If I am saying let us consider here to here, this distance is delta. Let us consider. Right? That gap between these two plates, let us consider that is delta. So same thing we can say for the layer which is at y is equal to delta. So at y is equal to delta also, at y is equal to delta, let us consider this plate having velocity capital U. Right? Let us consider this plate having velocity, let us consider this is the capital U. So same thing we can say for layer which is present at y is equal to delta. So at y is equal to delta, that U is equal to UP. U is equal to at y is equal to delta, U is equal to UP. right? Here this UP is bottom plate velocity, here this UP is the bottom plate velocity, and here this UP is the top plate velocity, right? So here also we can say there is no relate at y is equal to delta also, at y is equal to delta also, no relative velocity between plate and the fluid, right? Now when there is a relative velocity, please try to understand the things. When there is a relative velocity, then the sleeping of when there is a relative velocity, then sleeping occurs. When there is no relative velocity, there is no sleeping, right? If I ask you one very simple question, tell me, na? If I ask you very simple question, let us consider this is the block A and let us consider this is the block B. Block A is moving with the 5 meter per second and block B is also moving with the 5 meter per second. So tell me guys, in between the block A and block B, sleeping occurs, right? Both the blocks are moving with the same velocity. Both the blocks are moving with the same velocity. So tell me, there is sleeping between A and B occurs or not? No, there is no sleeping, right? There is no sleeping. There is no sleeping. Why there is no sleeping? Why there is no sleeping? Because no relative velocity. No sleeping between A and B. Why there is no sleeping? Because no relative velocity between A and B. Right? Same thing is here. Same thing is here. If I say y is equal to 0, the fluid layer velocity is equal to plate velocity. That means there is no relative velocity between plate and the fluid. The same thing is applicable here also. Same thing is applicable here also. Right? Therefore, these conditions are called no sleep conditions. Right? Therefore, these conditions are called no sleep condition. No sleep condition. Getting my point? Why this is called no sleep condition? Sometime in an interview, this question is asked. Right? Interviewer asks you, what is the fluid layer velocity at y is equal to 0? What is the fluid layer velocity at y is equal to 0? And you are saying, sir, the fluid layer velocity is 0 at y is equal to 0. Interviewer asks, why it is 0? Then you are saying the plate is stationary. You are saying bottom plate is stationary. Bottom plate is stationary. That's why this layer also having the velocity of the plate. That means there is no relative velocity exists between the plate and the fluid layer at y is equal to 0 and at the same time y is equal to delta. And if there is no relative velocity, that means there is no sleeping. Sleeping occurs when relative velocity is present. This is very simple funda. Sleeping occurs when there is a relative velocity. When there is no relative velocity, there is no sleeping. That's why these conditions is called no sleep condition, right? So beta, it is very much clear. If I ask you what is the velocity of this fluid particle, if I am talking about this particular fluid particle, what is the velocity of this fluid particle? If I am saying, let us consider this is the fluid particle A, and if I am saying, let us consider this is the fluid particle B. So if I ask you what is the velocity of fluid particle A and what is the velocity of fluid particle B, can anyone tell me? If I ask you what is the velocity of fluid particle A and what is the velocity of fluid particle B, can anyone tell me? The fluid particle A is 0 and the fluid particle B velocity is equal to capital U. Right? This particle having velocity of the top plate, that means particle number B having velocity that is equal to U, and the particle number A having having velocity which is equal to the bottom plate velocity. And since bottom plate velocity is stationary, therefore particle A velocity is 0. This is the stationary plate. Now this plate is stationary. This is the stationary. This plate is stationary. Okay, now see here. The line joining particle A and particle B. The line joining particle A and particle B. This is called beta timeline. Right? This is called timeline. Line joining particle A and particle B. This is the timeline. So beta, this is the timeline at time tau is equal to 0. This is the timeline. This is the timeline at tau is equal to 0. Right? Now, when time tau is equal to 1 second, when time tau is equal to 1 second, then this particle B is somewhere here now, because this particle B is moving with the velocity of capital U. So when time tau is equal to 0, the particle B is here. This is the timeline. When time tau is equal to 1 second, then this particle B reaches to here. So I am saying this is, let us consider this is the B dash. Now time tau is equal to 4 seconds. This particle B is somewhere here. So let us consider this is the B double dash. And if I draw the timeline, see here. This is the timeline at tau is equal to 1 second. This is the timeline at tau is equal to 4 seconds. Next, this is the timeline at tau is equal to 5 seconds, and so on. And so on. B triple dash. Okay, so what happened here? When you applying the shear load, please try to understand the things. When you applying the shear load on a fluid, it will try to resist the shear load by showing some deformation, by showing some continuous deformation. When you are applying the shear load on a fluid, it will try to resist the shear load, or it will try to resist the shear force by showing some continuous deformation. Beta, this is nothing but the continuous deformation. See, this is continuous deformation. If I am talking about the angle here, if I am talking about the angle here the angle is phi, then angle is phi dash, then this angle is phi double dash, and so on. So in case of fluid, when you are applying the shear load, in case of the fluid, when you are applying the shear load in fluid, when we apply the shear load, it will try to resist the shear load. It will try to resist the shear load by showing some continuous deformation. By showing some continuous deformation. And this continuous deformation is nothing but the flow. If someone asks you what is the flow, right, till the time we are not at that stage to define the fluid, till the time we are not define the fluids, right? And don't say fluid has the ability to flow. Don't say like this, right? Because this is a 7-8 standard definition. If someone asks you to 7-8 standard student, what is the fluid? And that student says, sir, anything having the ability to flow, that is a fluid. But from the engineering point of view, so you are engineer. So don't say this definition, right? Fluid is flowing, that is a property of the fluid, right? So see, so in case of the fluid, when we apply the shear load, it will try to resist the shear load by showing some continuous deformation, right? Now in case of fluid, in case of fluid, we can say the shear stress is directly proportional to shear strain rate, or angular deformation rate, because here the angular deformation is continuously changing with respect to time. In case of solid, when you are applying the shear load in the solid, this theta is not changing with respect to time. Corresponding to particular value of the f, this theta is unique. This theta is constant corresponding to particular value of the f. When you change the f, then this theta will change. But here this theta is continuously changing with respect to time, right? So shear stress experienced by the fluid layer, right? The shear stress experienced by the fluid layer, that is directly proportional to the shear strain rate, or we can say angular deformation rate, and that is nothing but the d phi by dt. So in case of the fluid, we can say tau is nothing but the shear stress experienced by the fluid layer, right? Shear stress experienced by the fluid layer, this tau is directly proportional to d phi by dt. Is it clear? But in case of solid, shear stress is, directly proportional to shear strain, or angular deformation, right? So shear stress is denoted by tau, and this is angular deformation. So here also I am saying this is phi, right? So in case of the solid, we can say the shear stress tau is directly proportional to phi. Tau is directly proportional to phi. Is it clear, everyone? Till this point, it is clear to everyone? Tell me fast, guys. Till this point, it is clear to everyone? Clear or crystal clear? Clear or crystal clear? Clear or crystal clear? Clear or crystal clear? Ruby, clear? Okay, fine. So in case of the solid, the shear stress is directly proportional to the shear strain. This is called Hooke's law. And in case of the fluid, shear stress experienced by the experienced by the fluid layer is directly proportional to the shear strain rate or rate of angular deformation or angular deformation rate. This is called Newton's law of viscosity. This is called Newton's law of viscosity. This is called Newton's law of viscosity. Right? So this is the Hooke's law and this is the Newton's law of viscosity. So in case of the solid, the Hooke's law play very, very important role. Right? In case of the solid, that Hooke's law play very, very important role. So whatever the role played by the Hooke's law in solids, the same role is played by the Newton's law of viscosity in case of the fluid. Right? Now see here, if you remove the proportionality sign, then the proportionality constant come into picture. If I remove the proportionality sign, then the proportionality constant come into picture. Let us consider that is C into phi. Right? What is the C? That C is the proportionality constant, and beta this C, this is the proportionality constant. This is the proportionality constant, and this proportionality constant depends on the type of the material. Right? This proportionality constant depends on type of material. If there is an aluminium, this C is different as compared to if material is copper. Right? So this constant is the material property. It depends on the type of material. Are you getting my point? Right? And this C is called shear modulus or modulus of rigidity. Right? This is the proportionality constant. This depends on the type of material, and this is called beta shear modulus or modulus of rigidity. Shear modulus or modulus of rigidity. Shear modulus or modulus of rigidity. Right? And it is denoted by, right? It is denoted by G. Right? So we can say solid, fluid. So we can say tau is equal to G multiplied by phi. Tau is equal to G multiplied by phi. Right? Modulus of rigidity or shear modulus. Right. Now come to the fluid. Now again, see here, if you remove this proportionality constant, if you remove this proportionality sign, then proportionality constant come into picture. Right? Tau is equal to C multiplied by d phi by dt. Right? What is C? C is the proportionality constant, and in the case of the fluid, this C depends on the type of the fluid. This C depends on the C is the proportionality constant, and it depends on type of fluid. That means beta it is a fluid property. Yes or no? Yes or no? It depends on the fluid, na? The C is a proportionality constant and it depends on the type of the fluid. That means it is a fluid property. Right? And this fluid property is known as the viscosity or dynamic viscosity or absolute viscosity or coefficient of viscosity right? Viscosity or dynamic viscosity or absolute viscosity or coefficient of viscosity, and it is denoted by a Greek letter, that is mu. So we can say tau is equal to mu d phi by dt, d phi by dt. Is it okay? Right, so this is the third difference, I think, right? See here, this is the first difference, this is the first difference, this is the second difference between solid and fluid, this is the third difference. Solid resists the tensile load by showing some deformation, by showing some definite deformation. Fluid never resists the tensile load. This is the fourth difference. This is fourth difference. This is fifth difference. This is fifth difference. Right? Now come to the difference number 6. Come to the difference number 6. Difference number 6. Now tell me guys, in case of the solid, or I'm talking about the, let us talking about the fluid. In case of the fluid, total deformation is important or rate of deformation is important? Tell me. In case of the fluid, total deformation is important or rate of deformation is important, or total angular deformation is important or rate of angular deformation is important? Which one is the important in case of the fluid? Tell me. No beta. In case of the fluid, the rate of deformation is important, not total. In case of the fluid, which one is important? See, d phi by dt is important, right? In case of the fluid, rate of deformation is important. Rate of deformation is important, right? In case of the fluid, rate of deformation is important, whereas in case of the solid, now tell me, in case of solid, what is important? In case of the solid, total deformation is important. In case of solid, total deformation is important. Total deformation is important. Right? In case of the solid, total deformation is important, whereas in case of the fluid, rate of deformation is important. See here, in case of the solid, phi is important, whereas in case of the fluid, d phi by dt is important. Okay, now come to the last difference. Solid regain its shape and size. Solid regain its shape and size when load is removed. And we are assuming load is applied within the elastic limit. Here we are assuming, when we write this difference, so here we are assuming whatever the load you applied on a solid, that load is within the elastic limit, right? So within the elastic limit, when you remove the load, within the elastic limit, when you remove the load, solid will regain its shape and size. Solid regain its shape and size when load is removed. 7. Fluid never regain. Fluid never regain. Fluid never regain. Or fluid never regain its initial position, I can say. Its initial position. Fluid never regain its initial position. Okay, so these are the differences between the solid and the fluid. Now we are at the stage. Now we can define the fluid. Now we are at that stage, we can define the fluid. So far, we are not able to define the fluid. Right? So far, we are not at that stage to define the fluid. Now we are at that stage after knowing the differences between the solid and the fluid. Now we are at that stage to define the fluid. Are you getting my point? So far, I'm not writing or I'm not explaining any definition of the fluid. Now, after knowing the difference between the solid and the fluid, now we can define the fluid. Now we are able to define the fluid. The fluid is a substance. See, the fluid is a substance. What is the fluid? If someone asks you what is the fluid, what is the fluid? So fluid is a substance. What is the fluid? What is the fluid? What is the fluid? Fluid is a substance. Fluid is a substance. Fluid is a substance which deform. Which deform. Fluid is a substance which deform continuously. Which deform continuously with respect to time. With respect to time. Fluid is a substance which deform continuously with respect to time under the action of shear load. Under the action of shear load. How small that shear load? How small that shear load? How small that shear load doesn't matter. How small that shear load doesn't matter. Right? This is the definition of the fluid. This is the definition of the fluid. Right? Fluid is a substance which deform continuously with respect to time under the action of the shear load. And why this continuous deformation occurs? Why this continuous deformation occurs? Because fluid try to resist the shear load. Right? Fluid tries to resist that shear load by showing the continuous deformation. Are you getting my point? Right? So fluid is a substance which deform continuously with respect to time under the action of shear load. How small that shear load doesn't matter. Right? Shear stress may be as small as possible. Right? Now, see, fluid, gases and liquids, right? Gases, and see, this continuous deformation is called flow, no? Continuous deformation. Continuous deformation is called flow. Continuous deformation is called flow. Right? What is the flow? The flow is nothing but the continuous deformation of the fluid. That is the flow. Right? Liquid and gases shows continuous deformation. Shows continuous deformation. Liquid and gases shows continuous deformation. Therefore, liquid and gases are considered as fluid. Right? Therefore, liquid and gases are considered as fluid. Okay, so whatever we discuss in today's class, that is clear to everyone. Whatever we discussed in the today's class, that is clear to everyone. uh, I think DPP will be upload in the I think app, physics wala app. Okay, so today's first lecture, right? Today lecture is first lecture, so there is no assignment problem or no DPP problem, right? But in future, definitely you will get the assignment problems, and definitely you are getting the daily practice problem. Yes, this is the first lecture of FM only. This is the first lecture. Okay, so thank you so much, guys. Bye bye. Take care and have a good night, everyone. Thank you so much.